Well, welcome back, everybody. I see our classroom is getting smaller and smaller as the semester progresses. Normally, that's about right. It's about halfway done class. Half through the semester, I end up with about the number that we have here. Anyway, let us continue. Any questions before I continue with that chapter? It looks like we've been on this chapter forever, but we'll be done with it today. Any questions? No? All right. Well, let me proceed. We were talking about chemical bonds. We talked about the two types of bonds, ionic bond and covalent bond. Okay. And so from that information, we went on to make Lewis dot structures of the atoms, which was basically just how many valence electrons they have. And again, I repeat, that's only good for the A elements, so Roman numeral 1 through 8A, because we know for sure we can predict how many valence electrons they have based on their position in our product table. Then with that information, we then went on to start making actual structures. And what we do is you're given a formula, you're told, you're given who is the central atom. Remember, and the way things work is we have a central atom, and everything, all the other atoms are bonded relative to the central atom. So we draw a line to represent a bond. We're talking about here covalent compounds, okay? Not ionic compounds. Ionic compounds, as I stated, are not a true bond, but we call them a ionic bond, and it's an electrostatic attraction, like two magnets coming together. Covalent bonds, there's an actual physical sharing of electrons. We're going to learn about this, and I touched on it, meaning that sharing is either going to be equal sharing or not unequal sharing. Okay, so you're given the formula, and all the other atoms are bonded to the central atom. Okay, so what we did was then add up the valence electrons that all of the atoms to the compound bring to the table, so to speak. Okay, so in this case, we had HCN. Hydrogen brought 1 valence electron. Carbon brought 4 because it's in group 4. Hydrogen's in group 1 valence electron. And nitrogen's in group 5, and therefore had 5 valence electrons. So we have a total of 10 valence electrons to work with. And this is important. That's it. You got 10 valence electrons. You can't just magically add more or take out. That's what you got to work with. And normally what I do is you have a number divisible by 2. So I just divide it by 2, and that tells me how many pairs of electrons we have, how many bonds, single bonds that we can make. Okay. It's just for me, it's a bookkeeping thing. It's easier for me to keep track of pairs than all these dots. With 10 dots, 10 electrons, not a problem. But when you get into 32 and greater, then you got to be careful of your dots. So just make them into pairs. This makes it a little easier. So we got 5 pairs to work with, no more, no less. So we're going to make that happen. And so then from there, we took the central atom that has been identified. Then we draw a line to everything else is bonded to the central atom. And that took care of whatever number of pairs. For this one, it took care of two pairs. 1 for the hydrogen, 1 for the nitrogen. And then what is left was 3 pairs. And now you can place them anywhere you want, except you can't place them on hydrogen, because hydrogen is now happy. Hydrogen will always, 100% of the time, only have 1 single bond. That's it. So the other atoms can have more. You can keep adding electrons until you get that happy 8. That's another thing. Hydrogen, 2, that's it. Everybody else, we got to put those electrons around wherever until we get that magical 8. Not 10, not 6, but 8. And that's our driving force, trying to arrange what's left over so that we can put them together to have 8 around all the atoms except hydrogen. What you do, if necessary, is then start to create either a double bond or a triple bond. That's it. All covalent bonds are either single, double, or triple. And you move these electrons around and share them to make a double bond. And then look at the octet, also keeping track of what you started to work with, and which was 5 pair. Can add more, can add less. You got to keep track of that. It's important. So finally, you adjust them, and we ended up with that particular formula, where a structure where we actually had the carbon in the center, which was the central atom. We had a triple bond to the right, and that triple bond was being shared with the nitrogen. Okay, the nitrogen had a lone pair on it, so those 2 dots represent the lone pair on the nitrogen. You can put 2 dots or you can put a line, whichever works. And then to the left of the carbon, we had a single bond. So if we look at each atom individually and count the number of electrons around that individual atom, you see that you have nitrogen has 8 electrons around it. 2 of them are on it and not bonded, and the other 6 are shared and bonded as a triple bond with carbon, okay? And that's why we can count them both toward carbon and toward nitrogen. If we look at carbon, we see again that triple bond being shared with nitrogen, so that accounts for 6 around carbon. And then to the left of carbon, there's a single bond with the hydrogen, and that counts for 2 more. So carbon now, it's happy with its magical 8 octet rule is fulfilled for both the carbon and the nitrogen. And obviously the hydrogen with its duet rule, it's happy. We count up all the pairs, we still have 5 pairs. We didn't lose them along the way. And so that's good, because that means we start off with 10 valence electrons and we ended up with 10 valence electrons. And I checked at each step, because you can very easily lose a pair someplace, as just as important as you can very easily add a pair mistakenly. So keep track of it as you go along. So that becomes a structure. And then from that information, once you know that, we then are able to identify the general formula. Remember, my mouse. Give me a second. My mouse is not responding. I've been having some electronic challenges lately. Let's see. Okay. Now. Well, so much for that. It's not working, so I'll fix it later. So we have the general formula of A, B, and E, okay, that we're going to use. And first, looking at the formula we come up with, we got A, there's always A, okay? And then we got B with the subscript of 2, and this 2 represents a subscript. I don't have the subscript function. And there is an E, E is the number of valence electrons on the central atom. And in this particular case, we don't have any. And so the general formula is AB subscript 2. We take that information, then we go to the shapes table. Okay, and we go and look for AB2 subscript 2, which is the first entry right there. And then the second column tells us the general geometry. We have the name, which is linear, and then that bond angle, which is the bond between the 2 other atoms that are bonded to the central atom, that angle, which is 180 degrees. Okay? That is how we utilize that. All right, so now that brings us to Lewis dot structures for polyatomic ions, okay? Now, we use the same process. The only difference is these are ions. And normally, these ions that we're working with, let me direct you back to the periodic table. And if you look at the periodic table on the bottom left, we have a table labeled most common polyatomic ions. So these are packets. We emphasize this. These are packets of covalent bonded moieties. They're put together, but overall, they have a charge. Therefore, that's why they are called ions. The majority of them have a negative charge. They're anions, and you can see there that they have a superscript negative on their structure, okay? Like I stated, majority of them are covalent bonded, but overall they are ionic, and therefore a lot of them are soluble in water, very, very polar, as we call them. So now we're going to start making Lewis dot structures for these type of ions. The procedure is the same, exactly the same, with one additional factor. And that is depending on the charge, be it negative or be it positive of the ion, we're going to either add or subtract a number to the total number of valence electrons that we have. And then at the end, we put a bracket, not a parenthesis, a bracket around it to designate it as an ion and with its respective charge. Okay, so let's do an example. Okay, so we do the same 4 steps, but we take the charge into account, okay? If that charge of that ion is negative, we're gonna add a number to it, okay? Because we have to account for that overall charge that ion has. And if it's positive to the ion, the valence electron count, we're going to subtract a number. The magnitude of that number we add or subtract is dependent on the charge of the ion. If the ion has a -1, we subtract 1. If it has a -2, obviously we subtract 2, etc. And the same is true for plus. If it's a positive plus, we add 1 or +2, whatever it may be. Okay. Then we, at the end, we come up with a structure like we normally would. Okay, we can even give it the general formula ABE and give it its geometry and a bond angle. And then after we're done, we just write it, the structure, and we put a bracket around it. And then upper right-hand corner, we add the charge, whatever the charge may be it negative or be it positive. Okay. Let's try, for example, this salt. That's the first cation ammonium ion that we have. This is derived from, actually from ammonia, okay? And 1 second. Okay, everything is working. All right, so let's try NH4, okay? This is the ammonium ion. Let's go back to demonstrate where it's at. We're not throwing it at you anything that's far-fetched, I hope. That there it is right there. It's one of the most common polyammonium ions that we utilize. It's called the ammonium, okay? Again, these polyatomic ions, we're going to use them later on. They come in a packet. We need more than one. We just put a parenthesis around it and we put a subscript to tell us we need more. We need 2, 3, 4, whatever, okay? Okay, so let's do its Lewis dot structure. So we do keep in track, keep in mind it has a positive charge, so it's a cation. So being a cation up here is positive, we're going to subtract a value for the ions that we created. So in this case, we have one nitrogen, which brings in 5 valence electrons, and there's 4 hydrogens, which brings in 4. Now, if we were not to forget that we have a positive ion, we may forget to add or subtract that -1. If we do, we end up with 9, right? And remember, I told you all the valence electrons will end up with a number which is divisible by 2. Now, we'll continue here. We'll do this, and we'll do a what if to help you out here. So we subtract 1, so we end up with 8 valence electrons, okay, or 4 pair. Nitrogen is a central atom, okay? Nitrogen is a central atom, so we can very quickly write nitrogen, and then there's 4 hydrogens, so we can quickly just do this. And guess what? That took care of 4 pair. We have 4 pair, and we're done, okay? Now, after that, because it is a polyatomic ion, once we're done, we can put a bracket. This is the bracket like this, and then we put the charge in the top right corner, okay? With respect to the general formula of A, B, X, and E, Y, well, we can do the same thing, and like we've been doing before. A is nitrogen, so it's A. And B is the moieties bonded to the central atom, which in this case is 4. And so that's it. We don't need to put an E because there's no lone pair. So this is our general formula. And now you can go to the shapes table and determine its geometry, which would be tetrahedral with the bond angle of 109.5. I'll let you do that, okay? Now you might ask, well, what happens if for example, down here, I added 1, okay? Instead of subtracting, I added 1 by mistake. So that means I got 10 electrons rather than 8 or 5 pair. Okay, let's go through that scenario. All right, so now I do the same thing, get nitrogen. I can do my hydrogens like I've been doing, like I did earlier. And that took care of my 4. I subtract 1, that means I got 1 pair left. Now, where can I put that 1 pair? I can't. That 1 pair that I have is extra that I mistakenly added because instead of subtracting, I added. Okay, it's a positive cation, so I subtract. If it's an anion, I add. Okay, so this tells me here that if I went the other direction, I end up with 1 electron. I can't put that extra pair on any of the nitrogens because they're full. Okay, nor can I put it in the nitrogens because the nitrogens got 4 or 8 around it. So that should give you a flag. Flags. Oh, maybe I did something wrong. So you go back here and realize, okay, I must subtract rather than add. Okay, so that helps you out because sometimes we tend to forget. All right, if it's negative ion, I gotta add a number. If it's positive, I gotta subtract. Okay. All right, so that's the structure, and that's what you write, and that is the polyatomic ion of the ammonia. Okay, with this structure, which is geometry, which we said was AB4. Okay, AB4 meaning that then we go to the shapes table. Shapes table, AB4 right there. So the ammonium ion would have a tetrahedral shape and a bond angle of 109.5. no different than the ones that we had done earlier that are not ions. The only difference are three things. One, we either add or subtract the number. Two, we put a bracket around the formula. And three, we put the charge in the top right corner. That's it. Compared to the non-ions. All right, let's try this one. All right, what they are right now, not important. What's important is you recognize we got PrO3, and it's got a negative charge. It's a polyatomic ion, okay? Very unusual. Bromine, yes, bromine can be the central atom for some compounds. And we're gonna work through it. So we got bromine 1 and 3 oxygens plus a negative charge. Okay, so the bromine being in group 7 brings in 7 valence electrons. Okay, there's 3 oxygens, each one bringing 6, so we have a total of 18 oxygens. Now we add a plus 1 because we have a negative charge on that ion. So that gives us a total of 26 electrons or 13 pair. And so I can very quickly say, all right, so we got bromine in the center and we got 3 oxygens right there. All right, so that's 3 pairs that we took care of, and we got 10 pairs left over. So where do you want to put them? Makes no difference. We can, like I said, start always on the outside atoms, fill them up with the 8 and just continue until got everything filled up. I got 10 to work with, so I can just go 1, 2, 3, 4, 5, 6, 7, 8, and 9. That took care of 9 pair, and that means I got 1 pair left over. Okay, well, I cannot put them on the oxygen because they're all of them are happy. The bromine only has 6, so I can very quickly just place it right in there. And it's not right now, everybody's all doing good with respect to the octet. Okay, I can do the general formula like normal. A is for the bromine, Br3 because 3 oxygens, and then we have a lone pair on the central atom, so we can give that general formula, Ab3E. Going to the shapes table, we can actually define that shape. And then since this is a polyatomic ion, I want to put a bracket around it, and then its charge, which was a negative, okay, on the upper right corner. So that is what we come up with for this particular polyatomic ion. There it is. Okay, Ab3E. Well, what do we do if we need to define the shape? Ab3E down here, trigonal pyramid. Right there, no different than ammonia, NH3. Remember we did that before? So there it is. Okay. All right. Let's try the one in the bottom. Sulfate, SO4. That's called sulfate. Top one is called bromate, BrOMATE. This is sulfate. It's one of the polyatomic ions on your table. Okay. Sulfur is the central atom, and it has a -2 charge. It's an anion, so we're going to add 2 to our final count of valence electrons. Sulfur brings in 6. There are 4 oxygen. Each one brings in 6, so there's 24. Okay, and then we add a 2 because it's a -2 charge, so we have a total of 32 valence electrons or 16 pair. And we continue to it just like with sulfur is underlined, so that is the central atom. So we write that. We got 4 oxygens, so I can very quickly draw 4 lines and connect the 4 oxygens. And that took care of 4 pair. Okay, so I got 12 here to work with now. So I can put them around the oxygen. So I got 1, 2, 3, 4, 5, and 6. 7, 8, 9, 10, 11, and 12. And that took care of all of my electron pair. It is a polyatomic ion, so I can draw, don't forget to draw the brackets with the -2 charge. Okay, I always circle my charge just to show it's in charge. That's a preference, it's not required. General formula, well, we got A, and B is simply 4, okay, which is no central electrons, no electrons in the central atom. And so that, if you go look that up, that is tetrahedral with 109.5. Okay. Now, let's say you forgot, you can go through the exercise and let's say you forgot to add 2. You end up with 30, okay, electrons to work with, or 15 pair. Well, if you go through that exercise, you're going to end up short of valence electrons. And so that tells you, I got a problem someplace. Okay, so, or if you add it, you're going to have too many electrons. So check your numbers here. Let me clear this up. Check your valence electrons. And remember, when they're anions, you add whatever charge they have. All right, so that is what we came up with. And then this is similar to the HCM we did earlier, but this time it's an ion. This is called the cyanide. You've heard of potassium cyanide, sodium cyanide. This is the ion. And the same scenario we did before. You got 4 valence electrons coming from carbon, 5 from nitrogen, and then 1 because of the negative charge. So we end up with a total of 10 valence electrons, or 5 pair. Again, here, there's neither one is a central atom. Carbon, nitrogen is only 2. So either one you pick is fine. You should end up with this particular structure with a lone pair on both 1 on carbon and 1 on nitrogen. Its structure here basically be AB2. I mean, it's just, both of them it's linear. Anytime you have 2 species together, you got a linear species. It's only 2 things being bonded. Okay, so that is how you do polyatomic ions, just like you do the covalent neutral compounds. The only difference is you account for the extra negative or subtract for the positive for the ion, add the bracket, and then put the corresponding charge in the top right bracket. Okay. All right, which brings us to this thing called valence shell electron pair repulsion, or AKA VSEPR. Okay, nothing fancy here. Okay, I kind of introduced it to you and explained to you. Notice that as we've been doing Lewis-Dot structures, I don't know if I recorded all this. What the heck? I forgot to put the video on. We'll find out. All right. You may have noticed that I mentioned to you, like if you got a lone pair anywhere in any atom, that they tend to take up more space because you got 2 negative, they're not bonded. So electrons tend to take up space, okay? And so they affect the structure, the overall structure of the molecule. And that's basically what's happening here. You're talking about the valence shell electron pair repulsion model, and how electrons, by repelling each other, affect the overall structure of the molecule, and then affect such things as properties of the molecule. Okay, this is nothing new here. I just introduced it earlier where we talk about ABE, where A is the central atom, B is the outer atoms, and E is any lone pair or pairs on the central atom. Okay. When you have a diatomic species, it's linear. It's got to be. Nothing else around it. You got 2 things bonded together. We got a linear configuration. Okay. When you have an AB2, which we did carbon dioxide earlier, again, here, this is a linear species, but be it 2 atoms or be it 3 atoms that are all bonded in such a manner, everybody's in the same line, so it's linear. You can have something called AB3, which we call trigonoplanar, okay? So the bond angle between all 3 bonds is 180 degrees. Here's an example of one. This is formaldehyde. I'm sure you're all familiar or heard about formaldehyde. This happens to be the structure of formaldehyde, okay? Cancer-causing species used to store that little pig you may have dissected back in high school, right? All right, so AB3, trigonoplanar. Everybody's in the same plane, 180 degree bond angle between all the 3 moieties, between the oxygen and the hydrogen.
Do you mean 120 degrees?
Yes, what did I say?
180.
Sorry about that. Thank you. 120 all the way around, okay? All right, good old-fashioned formaldehyde here. So that's the AB3 trigonoplanar configuration. Let's go to another one. Then this one I talked about, this is called the tetrahedral. And again, keeping in mind, the reason everybody has this particular shape is because that bond, there's electrons on that bond. So they want to put themselves in such a position that they are far apart from each other, okay? And they settle out tetrahedral. There's a 3-dimensional model of what it looks like. The electrons are the optimum distance away from each other. And so end up with the standard, this pretty standard configuration, the tetrahedral configuration, with that bond angle at 109.5 degrees. All right, another one is the bent, ABE, AB2E. We call this the bent. There is a lone pair on that sulfur. And you might look, maybe if you saw this and you say, well, wait a minute, okay, look at carbon dioxide, very similar structure, CO2 versus SO2. You might think, oh, man, they got the same structure. Well, the difference is this, okay, sulfur obviously is bringing, it's on a different group, so it's going to bring, there's going to be more oxygens, more electrons being brought. So carbon dioxide, because it's the carbon 2 oxygens, ends up with this particular structure, okay? Whereas sulfur dioxide has this particular structure. We actually have to make a double bond on one of the sulfurs and the oxygens. And there's a lone pair on the central atom. Well, again, as I mentioned, these lone pair, you may see it drawn with like a lobe of some sort. They take up space. The result is you would anticipate a 120 degree angle, much like the one we showed previously, but because they take up a lot more space, the bond angle here between the oxygens is compressed and pushed in, and therefore that bond angle is less than 120 degrees. Also, we have a very polar molecule here. We're going to learn a lot about polar compared to carbon dioxide, which is a nonpolar species, which has a big effect as far as properties and so forth. But we're going to learn more about that. Okay. That's the AB2E, aka bent configuration. We done the ammonia. Here's a bonnet. Here's a formula, space model field structure of ammonia. We have the lone pair sitting up here. Okay, they take up a lot of space, so that bond angle gets reduced right here. That bond angle, that if this was tetrahedral, would be 109.5, but because of the lone pair taking up space, it's squishing those other angles in, and we have a bond angle less than 109.5. Okay. Also, I also stated, whenever you end up with a lone pair of electrons on the central atom, you always end up with what we call a polar compound, Just like the previous example we did earlier, you saw that lone pair on the sulfur, you got a polar species. And we talk about polarity, polar, non-polar, think of it as oil and water. Polar is water-like. Non-polar would be more like oil-like. Okay, so this one here would be a lot more water-like with respect to properties. I'm not saying it's water. Don't misquote me. I'm saying it would have similar properties and it would be more soluble in water compared to a non-polar species. All right, so to summarize all this stuff here, it says, given any covalent molecule or polyatomic ion, you should be able to draw the electronic dot structure for it, okay? And from that information, once you do the electronic dot structure, you take the shapes table, create the general formula, and take the shape table and determine the shape, the geometry, and what bond angle, okay? So, go over the shapes table, and you might want to try pH3 and ozone. That's the formula for ozone. There's 3 oxygens. Give that a shot. See if you can do that on your own. And then we will, if you can't, bring it back to class and we'll go over it. Okay, try that one. All right, which brings us to a topic called bond polarity, which is related to electronegativity. Now, what I'm going to do is direct you to the canvas under the modules. Okay, under the modules, let me click better. Let me go back there. You have a module called additional resources. Okay. And first of all, let me explain about. Let's click shapes table. Molecule shapes. Let's click that. Simulation is brought up. Okay. And you can just do this. Select the first one. And what you do here, you can just double click on the single bond and you created a tetrahedral species. Notice how wobbly they are, because that is to demonstrate how the electrons repel each other at each bond here. And you end up with that tetrahedral shape, because on that bond you got electrons that are repelling each other. Okay, you got a double bond, so you can play with the different geometries here. Oh, let's do this to demonstrate how these electrons. Let's add one more, okay, and then we do a lone pair. Notice these electrons, they take a lot of space, so they kind of squish, increase that, decrease that bond angle. Okay, play with that one and give you a better idea on the different shapes and that you can see. But the other one that's important is called molecular polarity. Okay, this gives you a better picture when we're talking about polarity, which is related to electronegativity. Remember, electronegativity, unlike ionization energy, totally different. Electronegativity was a measure of the affinity for an atom to draw electrons onto itself when it's bonded, okay? And so let's take, for example, these 2 atoms. We got a bond here. I'm going to add what we call electrostatic. Now, right now, around A and B, they are equal with respect to electronegativity, meaning that that bond between them is equally shared, okay? The moment I increase the electronegativity on one of these atoms, then there's going to be a change in character. The redness starts, what happens to it is as I move, let's take B and we change the electronegativity. we increase its value electronegativity. Electronegativity is a value that all the atoms have. And if there's a bond between A and B has a higher electronegativity, guess what is happening here? It becomes more red in color. What designates it becomes more negative. The electronegativity increases, is drawing the electrons onto itself much greater than A is. The result is on A side becomes blue. And we also designate an arrow. You see that arrow on top? It's pointing toward B, and on the tail end is like a little plus sign. It's like a little, I'll show it, draw it here. The arrow points toward the more electronegative atom. So that is the direction of what we call a dipole. Okay, now you might say, I don't know what a dipole is, but I'm here to tell you, yes, you do. Does not a battery does not a battery have a dipole? Or better yet, the Earth. Are we not on the dipole? Yes, we are. Don't we have a North Pole and a South Pole? And two poles die, okay? Your battery, if you're operating on a battery right now, you have a plus and a negative on your battery, okay? Two poles. So in effect, what's happening here, when B increases in electronegativity, is drawing the electrons onto itself, it creates what we call a partial negative. That's what that symbol, that's lowercase delta, I believe, yes. A partial negative charge, not a full negative like the ions. The ions have a full negative charge. This is a partial positive side. Also on the other side, an A creates what we call a partial positive because the electron density is being pulled away, okay? And then we designate the direction the dipole is going to by an arrow. In this case, we draw the arrow toward B and we put a little plus at the end of the tail. And that is the direction of the dipole. We have created a dipole. Whenever you have a dipole in any bond, you have a polar bond, okay? Because you have a partial positive and a partial negative. As a general guideline, okay? Put this in long-term memory. Whenever you have, and I wish they would have used a different letter than B, but that's okay. I'm going to use X bonded to X. Whenever you have two atoms bonded together that are the same atom, you have a nonpolar bond. Nonpolar. Why? Because they're equal. They're equal in electronegativity. There's equal sharing. Okay. Whenever you have a bond that an atom that is different than, let's say, X, and I'm going to call that Y, you have a polar bond. It's a polar bond because one or the other has a higher negativity, either X or Y. That doesn't make a difference. I'm trying to demonstrate whenever you have two different atoms, you have a polar bond. There's only one exception. Long-term memory here. Whenever you see a carbon-hydrogen bond, you think, oh, they're different, must be polar. They're not. The electronegativity of carbon and hydrogen is so close to each other, they're basically nonpolar, okay? That's the only exception. And so you see anything like HCl, hydrogen chloride, polar, right? Anything else? If there's a carbon chloride bond, polar, okay? Automatically, that helps you to determine whether it's a polar bond or a non-polar bond. We're talking just about the bonds right now, because we're going to eventually look at the overall effect that each polar bonds on the molecule, which then would tell you whether the whole molecule is polar or not, depending on the type of bonds it has. But more on that, okay? The important thing here is electronegativity. This is what's happening. When you have a bond, one element has a higher electronegativity, you end up with a dipole, a polar bond, because the electron density is being pushed away. Now, I can reverse it. Right now, the arrow is going to the right. Let me clear the mess up here. But I can very readily reverse the arrow and make A more polar. Notice the arrow goes to the left, okay? And so whoever has more, the polarity is higher, we're going to create a dipole. When the polarity is the same, even if they're both high electronegative numbers, but they're the same, you got a nonpolar species, okay? All right. And what effect it does is, guess what? If I put an electric field on here, the electric field, the partial negative side is going to line up, is going to be attracted to the positive plate. Notice how it's happening there? All right. Okay. So this is bond polarity. And this is only for covalent compounds, okay? When covalent bonds, when the electrons are being shared equally, meaning that the electronegativity of each one is the same, we have what we call a nonpolar bond. No poles, no magnet, okay? When a covalent bond, when the electrons are being shared unequally, simply because the electronegativity of one of those atoms is greater, we end up with a pole, and specifically a polar bond, much like the poles of a magnet. In this case, we're talking about a charge. And this is all related to electronegativity. Recall that fluorine is the most electronegative element, okay? And we use that as a benchmark to determine the relative electronegativity of other elements, determined by how close they are to fluorine, because the trend is, as far as electronegativity from left to right of the periodic table, it increases. From the bottom to the top, it increases, all pointing toward fluorine, okay? Like this, here's fluorine. So electronegativity goes in that direction and in that direction as far as increasing. And so if we want to compare the electronegativity of, let's say, a bond between carbon and hydrogen, which one's more electronegative? Well, we find its position on the periodic table relative to fluorine. So for a carbon-nitrogen bond, nitrogen is much closer to fluorine than carbon is. Therefore, it's obviously a polar bond because they're two different elements, but we draw the arrow, the polar arrow, from left to right, because nitrogen is pulling the electron density onto itself much more than the carbon. And we draw the partial symbol, partial negative, on the side of the nitrogen, and a partial positive on this chart, the side of the carbon, okay? Polar bond. The only exception, okay, remember this, the only exception is a carbon-hydrogen bond. That is a non-polar bond, okay? No dipole there, no dipole whatsoever. Why? Because the electronegativity between the carbon and the hydrogen are essentially the same. So it's like having two atoms that are the same. It's equal sharing. Okay, so obviously noble gases don't have electronegativity. Why? Because we've got the bonds. They got octet fulfilled, or duet for helium. So the trend, as I mentioned, from left to right, top to bottom, all pointing toward fluorine. Fluorine's the most electronegative. Now, molecules with two identical atoms always 100% nonpolar bonds. So all of the diatomic elements have no fear of ice cold beverage. Remember that? All of them are nonpolar. Why do we need to know this? Because this is going to tell us down the road the physical properties relative to a polar bond. Okay, what type of physical properties? Because not only are we're looking at the bonds right now and how they interact with the atoms within the molecule, but that has an overall effect on the overall molecule, which then has an overall effect of the molecules interacting with each other, which then has effect on boiling point, melting point, surface tension, things of that nature. All of it related to the bonds and the type of bond it has, okay? So it's all tapped in together. Again, another nonpolar species is carbon-hydrogen bond. So it's considered to be a nonpolar bond, okay? So polar bonds are the result of two atoms that are different. And so if you see a bond with two different elements, automatically, unless it's carbon-hydrogen, it's a polar bond, okay? You don't have to go look anything up anywhere. You just see that you got two different elements, okay? Now, where you gotta look things up is where those two atoms are relative to fluorine, because then that's going to tell you which direction you're going to draw that arrow to, which is more electronegative. You don't have to memorize all the electronegative values for all the elements. Each one has each one has their own individual EN number, but it's not necessary to memorize each one. You just find its position relative to fluorine, okay? And so we draw the arrow, okay, we indicate the polarity in which direction. So the partial symbol, partial positive and the partial negative, that you put that on the atom, that the partial negative goes to the atom, which is more electronegative. So for the bottom left corner, you have a bond between carbon and fluoride. Automatically, as we stated, the fluoride is the most electronegative element out there. So there's really nothing to look up. Automatically, that fluoride has a partial negative, which means that the carbon has the partial positive. And the arrow goes from left to right, okay? We look at a bond between oxygen and hydrogen. Well, we're not sure which direction the arrow is. We do know it's two different elements. It's polar, but which direction? Well, oxygen is much, much closer to fluorine than hydrogen is. Find its position on the periodic table. Hydrogen is way in group 1, okay? Oxygen is pretty much closer. So it's more electronegative than hydrogen. Therefore, it contains a partial negative. Hydrogen has a partial positive. Arrow, in this case, goes from right to left. Similar scenario between phosphorus and chloride. Well, we see that the chloride is right below fluoride compared to phosphorus. So the chloride is a lot more electronegative. Therefore, it contains the partial negative symbol. And the phosphorus has a partial positive, okay? All right, we know about noble gases don't have EN, okay? They're just happy, got eight electrons around it already. All right, so fluorine is always the most electronegative species, remember that. So in this case, you may be given a bond and then ask, okay, write the delta notation, meaning the partial positive and the partial negative, and then write a polarity arrow in the direction the atoms are placed for you. So we have carbon and oxygen, okay? First things first, if I look through all these bonds here, I can see they're different atoms, okay? So automatically, I know I'm gonna have polar bonds, except this guy, check it out. Right, carbon, hydrogen. So we know automatically we got a nonpolar bond here. NP, nonpolar bond, no questions asked. Everybody else has two different atoms. Automatically, all those other four are polar. Now, but we need to decide in which direction the polarity goes. So that is where we find it, their relative position relative to fluoride, and we can write the arrow and the delta notation. Oxygen is a lot more electronegative. So we got the arrow going toward oxygen. Nitrogen fluoride bond, automatically fluoride. No questions asked, because fluoride is the most electronegative atom. Okay. We did oxygen before. Oxygen is a lot more electronegative, so we got the delta negative on the oxygen side. And then the carbon chloride, of course, chloride's a lot more electronegative than carbon, so it has the partial negative side. Okay. All right, and then finally, carbon hydrogen bond, none, because it's nonpolar. Okay. Nonpolar. And the same would be true if they wrote in here any of the diatomic elements, all 7 of them. All of them would be nonpolar. Question here, are the bonds ionic? Are they polar covalent or nonpolar covalent? Remember, we got 2 types of bonds. Okay, let me rehash this before we go any further to make sure you got this. We have the ionic bond, okay? And then we have the covalent bond, okay? And underneath the covalent bond, we have the nonpolar bond, and we have the polar bond, okay? Covalent bonds, there is sharing of electrons. Okay. Ionic bonds, there is no sharing of electrons. One's got a full-fledged negative and the other's got a full-fledged positive. Electrostatic attraction. Covalent bonds, there's a sharing, either equal sharing or non-equal sharing. And that is determined by the electronegativity of the atoms that are being bonded and shared, okay? And so if we have, in general, to remember, if we have an X, Y scenario, polar bonds. If we have an XX scenario, as far as a molecule being bonded, nonpolar bonds, including the carbon-hydrogen scenario, okay? And so here they're asking you ionic bonds. Well, ionic bonds, we know it's from a combination of a metal and a non-metal. And so sodium chloride is the only ionic bond here. Okay. The other ones are covalent. Now, to determine whether they're polar or non-polar, well, what do we see? We got bromine and bromine, Br2. They're both the same element, both the same electronegativity. They're equal sharing. Therefore, it's nonpolar. We got the phosphorus fluoride bond, automatically it's polar, 2 different elements, okay? They're not asking you to draw the arrow, but if you did, you'd be going in the direction of the fluoride. And then the fluoride carbon, bromide, which can happen with halides bonding together, it is a polar bond, okay? And in this case, here we have no dipole. Over here is going from left to right with partial negative on the fluoride and partial positive on the phosphorus. Okay, no polar bond, I should say no partial positive or negative on sodium chloride. Ionics don't have that. And over here it's going from right to left with the partial positive on the bromide and the partial negative on the fluoride. Okay. All right. So polarity, very important concept that we're going to be using over and over again. Okay, it's going to keep popping up over and over again, especially when we get to the part where we're dealing with physical properties called IMF, intermolecular forces, and how molecules interact with each other. Depending on the type of polarity of the molecule, we could have, we're going to be looking at boiling point, melting point, surface tension, viscosity. We won't be able to give you to determine absolute values. No, we're not going to do that. However, we will, we have a question here. Yeah, we will be able to do a relative comparison. We'll be able to look at a molecule and say, all right, who do you think, for example, let me give you an example why this is important. This whole thing we talked about. You could be given something like, here's water versus, let's say, chlorine gas, okay? Question may be asked, all right, which one has a higher boiling point, okay? Question number one. Question number two, which one would have a higher surface tension? Which one would have a higher melting point? Who's more viscous, okay? Which one would be more soluble in water? Obviously, water would be soluble in water, you know, things of that nature. And it's all related to the bonds that these molecules have, and whether it is a polar bond or a non-polar bond, okay? All right, so this whole thing will be popping up. So just think of that polarity, that bond, so simply a tug of war of bonded electrons. Okay, if it's an equal sharing, everybody's happy, they pull enough electrons to each other. But if you get unequal sharing, you end up with a little bit of a negative on one side and a little bit of positive on the other side. Not a lot, but not a full-fledged, but enough to call it a polar bond, okay? So here we have things like ionic, polar, non-polar bonds. So we know that metal, non-metal combination is a ionic bond, okay? Hydrogen and chloride. Okay, question number one, you ask yourself, H and Cl. They're both non-metals, so it's a covalent bond. They're both different, and they're not carbon and hydrogen, therefore it's polar. See how I went through that? Okay, hydrogen bond. They're both the same atom. It's a covalent bond. They're both non-metals. Covalent bond. They're both the same. That means they have a non-polar covalent bond because there's equal sharing in that bond. Chlorine and carbon, two different elements, automatically polar bond. Okay, and it's going in the direction, as far as the polarity direction is going in the direction of the chloride. Okay, so we got a polar covalent bond. Carbon hydrogen, that is the one example of different bonded elements or atoms that are non-polar covalent. Okay, oxygen and oxygen, covalent bond, they're both the same, like hydrogen, non-polar covalent bond. Potassium and oxygen, well, we got a metal and a non-metal. Automatically, it's an ionic bond. Okay. And then finally, phosphorus and fluoride, another covalent bond. It's especially polar. Why? Because we got fluoride. You know, makes it, every time you got a fluoride bond, very, very quickly you have a covalent bond. Okay, now if we needed to draw the delta notation and the arrow, well, none for the first one. The arrow will go from hydrogen to chloride, and it would be a partial negative on the chloride and a partial positive on the hydrogen, okay? None for the hydrogen, okay? None for the ionic compounds don't have that. Chloride, carbon, arrow goes from carbon to hydrogen. So partial positive on the carbon, partial negative on the chloride. None for the carbon hydrogen, none for the diatomic oxygen, none for the ionic compound, but definitely one arrow for the phosphorus fluoride in the direction of the fluoride, partial negative on the fluoride, partial positive on the phosphorus, okay? All right. We're almost done here. I hear a lot of dings. I'm losing people. All right, let's see where we at now. One more, couple more. So now, right now, we've been talking about the bonds themselves. Now, let's move it, let's expand it. Right now, talk about how the polar bonds affect the polarity of the overall molecule, okay? Now, as a general guideline, which is roughly 100% true, when a molecule has all polar bonds, all non-polar bonds, it ends up as a non-polar molecule. Let me do an example real quick. All right, let's do methane. Remember, we did tetrahedral. Yes. Okay. First of all, we have carbon, hydrogen, automatically non-polar bonds. We got 4 non-polar bonds. Everybody's non-polar. That means overall, you have a non-polar species molecule. This is methane. This is the structure formula for methane. Okay. And it is non-polar because all the bonds are non-polar. Obviously, any of the diatomics, H2, Br2, have no fear, ice cold beverage, all of them, non-polar bonds, non-polar molecule. Okay. Now these, let me explain this a little bit here because it can be a little bit confusing for people. That arrow that we used to designate the polar bond, okay? Now, I don't want to get into the details of this, but I just want to tell you this. If you're not familiar with this arrow represents what we call a vector, okay? For this part, it's not important, but what's important from this is this, the fact that it's called the vector. What that means is it has direction and magnitude, okay? Meaning some kind of value, some units. It has direction. So this arrow, that the way I wrote this, it could have 5 units. I'm just going to give you arbitrary units. And the direction is to the right, in the positive direction, okay? Now, I can draw another arrow in the opposite direction, okay? Also 5 units in the opposite direction, okay? It's not to scale, but let's say they're both the same. What happens is the result is they cancel out mathematically. Both of these equal to 0. Okay, if they were going in the same direction and each one's 5 units, then I end up with 10 units because they add the cumulative because they're in the same direction. Okay. But the main point is this: if they go in opposite direction, they cancel out. Let's take a look at carbon dioxide. We'll give that more detail. Do you agree that carbon dioxide has a polar bond on each side? What do you think? Between, let's say, look at the carbon and the oxygen. Would you classify that as a polar bond? What do you think? Looking from here to here. Polar? Yes. 2 different atoms, okay? It's a polar bond. There's a dipole. It's going from carbon to oxygen. And I can draw that arrow in that direction, okay? So I got a partial negative over here in the oxygen, partial positive in the carbon. And guess what? On the other side, I have another polar bond. Equal magnitude, but in the opposite direction. And like I stated down here, These arrows represent what we call vectors, which that part's not important, but you can recognize that the arrows have, since having direction and magnitude, and they've gone opposite directions, mathematically, they cancel each other out. So for carbon dioxide, they cancel each other out, which means I got a non-polar molecule. So even though I got two polar bonds in there, because they cancel out, I end up with a non-polar species. Sulfur dioxide, what we talked about earlier, we have a polar bond. But guess what? Because of those lone pairs on the central atom, that shifts that bond angle into much less than 120. It shifts it. It's not exactly linear like carbon dioxide. It shoves it down. We end up with a polar compound because the dipoles of each bond did not cancel out. Did not cancel out. They're going in different directions. If they were different directions, but this is going to the southeast and this was going to the, I guess, southwest. This one over here. To the left is going left and to the, because these have positive and negative direction. Okay. And so when polar bonds do not cancel out, they got more than one polar bond, obviously, you end up with a polar molecule. Okay. Let me give you another example. Let's take that methane that I did earlier before. I said, okay, we have hydrogen. I'm trying to draw it three-dimensionally. We all agree carbon, hydrogen, nonpolar bond, overall nonpolar molecule. But let's do this. Let's take one of those hydrogens and substitute it with a chlorine. And so here we have three nonpolar bonds and one polar bond, which makes this guy a polar species, okay? And if we continue to, let's say, replace the other hydrogen with another hydrogen of chloride, I still have a polar species. And if I do that to the third one, still polar, okay? Because these polar bonds are all going in different directions. They don't cancel each other out. The moment I replace the fourth one with another chloride, I end up with 4 polar bonds. And because of the geometry, they cancel each other out, all 4 of them. And so now I end up with a nonpolar bond, nonpolar molecule. Okay, once I replace all those 3 other hydrogens with fluorides all the way around. So in the tetrahedral configuration, if all of the species bonded to the carbon in the middle are the same other than hydrogen, they end up with a nonpolar species. I replace one with something else, I got polar, okay? All right, so. And when the polar bonds do cancel out, when the arrows go in different directions, like I said, these arrows represent magnitude and direction. When they go in opposite directions, that means they cancel each other out, meaning that carbon dioxide, though it has polar bonds, is nonpolar, okay? And so that's why putting it all together, when you're given the formula, you come up with a structure like we did for both of these, sulfur dioxide and carbon dioxide. Once you come up with that, then you identify the polar bonds and see if anybody cancels out. If anybody cancels out, you got a nonpolar species. If nobody cancels out, you got a polar compound. Okay, like the first one, sulfur dioxide. The polar bonds do not cancel out. Therefore, you have a polar molecule. Carbon dioxide, the polar bonds cancel out. Therefore, you have a nonpolar species. So these two, just based on the polarity of the molecule will have totally different properties, and we can determine down the road who's going to boil at a higher temperature, who's going to melt if it's a solid, who's going from solid to liquid into a higher temperature, who's going to be more viscous, and so on and so forth. Okay. So we gotta continue. We gotta remember how we did this, because when we get to that chapter, that's how we're going to be able to understand that particular chapter, due to the polarity of the bond, which is related to the polarity of the molecule, which is related to the physical properties of the molecule. Okay, for methane, I just talked about that. So they're all nonpolar bonds, so it's got to be a nonpolar molecule. Okay, now PCl3. If you have three polar bonds, there's three polar bonds, phosphorus and chloride, and you might think, okay, maybe it is trigonoplanar, where everything's in the same dimension and things cancel out. Okay, but it's not. We have to go use the Lewis dot structure to figure out the structure of this species, and if you do that, you end up with a lone pair on the central atom, which automatically tells you, boom, polar species, okay? Automatically, polar species, every time you got a lone pair on there. And then carbon dioxide, we talked about that. The lone pairs cancel out. Excuse me. The double bonds cancel out. You got lone pair in the brain. We have carbon double bonded oxygen. Okay. The polarity of each bonds cancel out. So we end up with a non-polar overall molecule. All right. So we did water, water, the structure that is, we ended up with this structure. It had two lone pairs on the central atom. And then we also did ammonia, also with two lone pairs on the central atom. Automatically very polar species. In fact, water probably is the most polar molecule out there. We use that as a reference point as far as whether something is soluble in water, because we know water is very polar, and then we use oil as the nonpolar example. So knowing the polarity of the molecule then allows us to determine whether it would be soluble in water, whether it would be more soluble in water or more soluble in the oil. And that polarity is very, very important for multiple of things we use in real life. Yeah. All right. So congratulations. We are done with chapter 7. Okay. Took a little bit of time, but we got there. All right, let me pull up, make sure I got my other one.
Thank you.
You're quite welcome. I'm debating, why don't we just, the next one is nomenclature, is like 24 pages. It's very short, very short. Why don't we continue with that next time, Thursday? We'll knock this one out and we'll jump into 9. Nomenclature, which is basically naming compounds, is very short, 24 slides. Okay, why don't we stop it here, and we'll continue with chapter 8, and work on your homework and whatever assignments. And then, you have any questions, comments, concerns?